So our next speaker is Colin Price, who's a professor in atmospheric sciences in the School of Geosciences at Tel Aviv University. His main field of research deals with global lightning activity and the connections between lightning activity and the Earth's climate. His work involves the relationships between lightning and forest fires, atmospheric chemistry, and severe storms, among many other areas. I had the pleasure to work with Colin when he was a graduate student at Columbia in the early 1990s. Colin was a pioneer in assessing how lightning might change with changes in climate and how that could influence lightning-generated fires at the ground. The 3 papers we wrote together have so far garnered more than 650 citations on Google Scholar. He's a leader in this field, and so appropriately, his talk is entitled Lightning and Climate Change.
Okay, so this presentation is about lightning and climate change. My name is Colin Price. I was one of Dave Ryan's PhD students back in the 1990s. And we were one of the first groups to try to understand how climate change may affect lightning and thunderstorms in the future, and including trying to model this to predict what may happen in the future, which we'll talk about in a few minutes. Lightning is, first of all, it's a natural hazard. Although it's part of thunderstorms, lightning, as you can see here in this animation, is dangerous to aircraft, aviation. In fact, the commercial aircraft that we fly in from going to meetings to see family get struck by lightning approximately once every year. But as you can see with this movie, the aircraft is not damaged. It's made out of metal. What we call a Faraday cage, and so actually aircraft are built to withstand lightning bolts, which have lots of current and actually get to very high temperatures, up to about 30,000 degrees, the temperature of the lightning channel. So aircraft is one major industry which is interested in lightning. Power companies are obviously interested as well, because we have lots of power outages during thunderstorms. Lightning can strike directly the towers, the cables, and surges from the currents in lightning can cause problems with computers, televisions, but also power outages. People are killed by lightning and injured. Most of the people are not killed, but get injured, and most of the damage is to the neurological system, because it's a lot of electricity going through your bodies. Tens of thousands of people probably are killed every year, although we don't have exact numbers, and it's probably hundreds of thousands are injured from lightning, even not from direct strikes. But like you can see with the animals on the bottom left, cows and livestock are often killed, whether they're touching a fence, which is an electrical conductor, or whether they're near a tree. And because they have 4 legs on the ground, you can actually develop a very strong potential between the front and the back legs, which can actually cause a heart attack for these animals. So lightning is definitely a natural hazard, and this is one of the reasons we want to study it and see how it may be changing as the climate changes in the future. And today we have a new problem with lightning, and that's wind turbines. When we're trying to look for renewable energies to replace fossil fuels, wind energy is one of the main sources. And because windmills and wind turbines are normally the highest point in the landscape, they often get struck by lightning, and they normally have a value of millions of dollars. And so one strike can actually take out a turbine and cause lots of damage. So now there's a whole new field of study trying to understand how we can protect wind turbines from lightning thunderstorms. Okay, when we're talking about climate and temperature, most people talk about temperature changes, global warming. When we look at actually changes in temperature on different timescales and lightning or thunderstorms, we see that generally most studies show a positive correlation between surface temperatures and lightning activity. The warmer it is, the more lightning we have. Colder it is, the less lightning. And these studies have been on different time scales, from the diurnal scale, hourly changes on a day-by-day scale, seasonal scale, El Nino scale, interannual scales. We don't have too much lightning data going back too far, and so we can't really look at climate change signals yet. And so we try to use proxies of smaller changes in the temperature to see how they impact thunderstorms and lightning. On the left, you can see a plot which is showing actually global lightning, the bold line, showing the global lightning, which is measured actually from a methodology we call the Schumann resonances, after German scientist Schumann in the 1950s. This is actually a global index of lightning, so it's not actually measuring the lightning discharges, but it's an integrated measurement of the magnetic field produced by lightning around the planet. Sorry, the lightning is shown by the white boxes. The solid bold curve is actually the temperatures. They're both actually, sorry, mistake. They're both labeled global lightning, but the solid one is the temperature shown on the right-hand side, the temperature anomaly. So not the absolute temperature, but the changes from the climatology, plus minus 0.5 or 1 degree. And on the left side, we have this index, which is related to the lightning activity, shown in the white boxes. And this is from January 69 to July 74. And this up and down in the temperature shown by the bold curve is actually the El Nino signal. During the El Nino, the tropics warm, so we have the warmer waters and the warmer air in the tropics during El Ninos, and the La Nina between the cooler temperatures. And the lightning activity on a global scale tracks this fairly nicely. And this was maybe the first indicator that global lightning is actually influenced by global temperatures. On the bottom right, we can see another estimate from some of my research, also looking at these global Schumann resonances shown at the bottom curve. Black, this is actually data measured in Antarctica, but it represents the electromagnetic waves traveling around the globe from lightning with a seasonal cycle seen from year to year. And the top curve is the temperatures from the MSU satellite, which represents the lower troposphere. It's not the surface temperature, the lower tropospheric temperatures, but again, we see the seasonal cycle of warmer temperatures in the northern hemisphere summer because we have more land in the northern hemisphere summer, and cooler temperatures in the southern hemisphere summer. And warmer seasons give us also more lightning on a global scale. If we look regionally, we can also look, say, just over Africa, the top plot, in South America, the bottom plot. Again, the black and the blue curves represent some global index of lightning on a day-to-day basis. So this is over a 62-day period in 1998. And the red curves in both plots represent the regional mean temperature, daily temperature over Africa and over South America, taken from the NCEP reanalysis, which is a combination of model and data, and we have data available. The correlation coefficients aren't that high, 0.5, 0.57, but they're both statistically significant, showing that generally when we have warmer days, the peaks in the red curves are matching with peaks in the blue and the black curves. Warmer days give us more lightning activity in the tropics. Cooler days, we have less lightning activity. So generally, we see a positive correlation on all time scales between changes in temperature and changes in lightning activity. So now the question is, what will happen in the future? So projected for the future, we have to look at different scenarios, generally from climate models, many climate models. And here, this is somewhat outdated already, but the results are more or less the same. The IPCC 2007 scenarios for the future for the different scenarios A2, A1 to E1. The orange curve is already out of date because it implies keeping the emissions constant at the level of the year 2000. Well, we've already passed that long time ago and the emissions are still going up. And if we go to the other scenario, the other colored curves, this represents the increase in temperature expected based on various scenarios of using alternative fuels or business as usual. And on the right-hand side, we can actually see the range of scenarios where some are even going up to 6 degrees warming global mean by the end of the century. Hopefully that won't be a correct scenario, but it's likely somewhere between 1 and 3 degrees by the end of the century. So what will happen with lightning? So for lightning, we have to somehow try to estimate this in the climate model, because climate models don't normally have a calculation for lightning or thunderstorms. They calculate convection, convective clouds. So part of my PhD, together with David Ryan, was to develop parameterization for GCMs, where we could take large-scale parameters supplied by the model from the convective clouds and estimate what lightning activity should be. And we use basically empirical relationships observed in the field to try to estimate what lightning would be. And what we see here in the plot is on the left-hand side, the two plots on the left side are satellite data of lightning. This is from the OTD sensor, or a NASA satellite, for 2 different seasons, June, July, August 1995, and December, January, February 95, 96, showing the distribution of lightning where the color represents more lightning. And on the right-hand side, we have our model simulations for the same months, June, July, August, December, January, February. But we're talking about climatology, the model climatology, compared with 1 year on the left, or 1 season. We would expect differences. Also, the observations are not perfect. These are from low Earth orbit satellites, which are taking a snapshot every time they fly over certain locations. So most of the time, they're not observing thunderstorms, and we integrate over some time to get this climatology. So we expect differences, but overall, agreement is not too bad. What we know now from the observations is that lightning follows the seasons. Most of the lightning is found in the summer hemisphere. So in June, July, August, most of the lightning is north of the equator, going up into Siberia, into Alaska. We also see this in the model. And in the southern hemisphere summer, most of the lightning is south of the equator, which we also see in the model, and mainly over the tropical land masses. This is something we actually learned only when we started to look at the lightning from space, that the lightning activity around the planet, 90% of the lightning is focused over 30% of the globe, which is the continents. This is also a topic we're still focusing on for research, or why do we have such little lightning activity over the oceans? Still an open question, but we think it's due to the solar heating every day, where the sun heats the ground, the solid earth, the land surfaces much more than it heats the oceans on a day-to-day basis. You have very small changes in ocean temperature, the water temperature, over a 24-hour period, where over the land you have very large changes, and that results in large instabilities which develop over the continents during the day, late afternoon in the tropics, which you don't have over the oceans. But the model does tend to simulate fairly nicely the global distributions, the seasonal changes, and actual amounts of lightning around the planet. Well, now trying to go into the future, we can then look at the changes in temperature in the future. And what we're seeing on the plots here are the changes in temperature given by color as a function of altitude or pressure and latitude, so from 90 north to 90 south, and for the different periods in the future from 2010 to 2030, 2046 to 2065, and towards the end of the century. The blues represent cooling in the stratosphere, and the reds and yellows warming. And what we notice is that the strongest warming is actually in the upper troposphere, in the tropics. And we have more warming in the upper troposphere than we have at the surface. Now, this would imply that actually the atmosphere would become stable. You have less convection, less thunderstorms, because when you warm up above, compared with the surface, you actually result in stabilization of the atmosphere. So this appears to imply that we would actually maybe have less thunderstorms in the future. But when we run the model, the climate model, into the future, we find that we actually, by the end of the century, we have about 40% more lightning activity, and it's actually in the places where we expect it to be over the tropical land masses. In this GISS model run, which was in the 1990s, we found most of the lightning increase would be over the maritime continent, over Southeast Asia. And exactly where we would expect the stabilization of the atmosphere, we actually have more lightning. And this appears to be somewhat of a paradox, that where we have a more stable atmosphere in the future, we're actually having more lightning. But, and I'll get back to that, but basically the sensitivity we find in many different model runs, different studies, is that for every 1 degree global warming in the model, we see about a 10% increase in global lightning. And these numbers have stayed fairly constant over the years, showing that this sensitivity is repeated, whether it's from observations, from models. We get this basically a 10% increase for every 1 degree global warming, although the local changes can be much larger. So while this 40% by the end of the century may be a global change, we can get much higher, 70, 80%, maybe 100% in some of the regions. So to talk about this paradox, that actually when we're getting this stabilization, we actually have more lightning, we can look at the present day climate. Some interesting things we see when we look at the present day climate, looking at rainfall and lightning maps. So on the top here, we have 10-year average rainfall from satellite. This is the TRMM satellite, Tropical Rain Measurement Satellite, which has both a radar, precipitation radar, shown on the top, and a lightning sensor, shown at the bottom, so that we have the same measurement from the same sensor at the same time, even though we don't have continuous measurements. Whenever we do have a measurement, we have the rainfall and the lightning together. And when we average this over 10 years, between 1998 and 2007, at the top we see the rainfall, the bottom we see the lightning with the colors. And we see something interesting here. If we rank the tropical continental regions for where we have the most rainfall and where we have the least rainfall, see that the wettest regions are over Southeast Asia, and then the Amazon jungle, followed by Africa. But if we look at the lightning, it's exactly the opposite. We have this most lightning over Africa, then over the Amazon, and then over Southeast Asia. We also have other latitudes, but it's integrated over the year. Generally, we have always in the tropics lightning, and Africa has the most lightning. And if we look at the boxes over the ITCZ, of the tropical oceans, where we have lots of rainfall, we don't have any lightning. This kind of backs up the paradox that when we look at climatological scale, not looking at an individual thunderstorm happening in the afternoon today at some location, normally the rainfall is linked positively with the lightning. The more rainfall, the more lightning, and vice versa. When we average over long periods of time over the climate, it appears that actually when we have too much rainfall, we have lots of rainfall, we don't have a lot of lightning. And it appears actually that lightning prefers drier climates. Where it's drier over Africa, we have more lightning activity. When we have very moist conditions, like over the Amazon jungle or over the ITCZ, then we have less lightning. And this is, we think, due to microphysical processes in clouds related to warm and cold rain processes, which maybe I'll come back to a little later. We can also look at the kind of analog for this paradox with the El Niño. The El Niño southern oscillation basically is a climate shift of the Earth every 3 to 7 years. This is what the Pacific Ocean normally looks like. We have the trade winds, which are pushing the warm waters to the western Pacific, where we have the warm pool of water shown in red. On the other side, we have the upwelling of cold water, and we have cold temperatures, maybe 10 degrees difference on the equator between the west and the east. Where we have the warm waters, we have lots of convection. We have lightning, we have thunderstorms. Where we have the cool water, in the dense air, we actually have the sinking, and this produces what we call the Walker circulation. Rising branch in the West Pacific, sinking in the east. This also impacts the ocean underneath, the thermocline, but we won't talk about that at the moment. This is the picture during December, January, February, which is normally when we have the peak of the El Niño. During the El Niño years, we have a shift in the convection, and everything moves eastward. The hot water, the warm waters move towards the eastern Pacific. We have the El Niño warm currents along Peru and Ecuador. The convection also moves eastward, and we have in the mid Tahiti and the Christmas Island lots of rainfall. This can even make it to the east coast of the Pacific or to Peru, Ecuador, producing lots of flooding and landslides. And over Indonesia, Southeast Asia, where we normally have the rainfall, we have dry conditions, very severe drought. Northern parts of Australia, Indonesia, which are often associated with severe forest fires. But now, if we have a look at what happens to the lightning in El Nino and La Nina years, the left panel shows the precipitation anomalies for those years. This is actually for just one El Nino and La Nina, so the winter, December, January, February, 97, 98, compared with 98, 99, the year latest. This is La Nina, where normally we get lots of rainfall in Southeast Asia, the blue areas, above average rainfall, compared with El Nino, where we have drought conditions, very dry conditions in the West Pacific, of the islands here, Borneo, Indonesia, Northern Australia. But when we look for the very same months at the lightning from the OTD, we see that we have 57% more lightning over this region during the El Nino compared with the normal situation, and less lightning during the La Nina, when it was very, very rainy. So this again matches with the paradox that very wet conditions give us less lightning and dry conditions give us a lot more lightning. How do we explain this? Well, maybe the way we think we explain this is maybe we do have less thunderstorms, implying less rainfall, but when we do have thunderstorms, they're much more intensive. And so each one gives us a lot more lightning activity, and when we integrate over the season, we have more lightning because we have much more powerful thunderstorms, but we have less water reaching the surface, less rainfall. And when we have lots of warm rainfall, lots of moist convection, but not very intense convection, we have lots of rain, but not very much lightning. It's not very explosive storms. This is a hypothesis which needs to be checked. It's been proved in some areas, but we need to study this further. Well, if that's the case, and we look at how rainfall may change in the future, here we can see the predictions of changes in precipitation by the end of the century, by 2099. December, January, February on the left, June, July, August on the right. The color shading shows you all the increases or the decreases, the increases in blue above zero, or decreases in the browns and oranges by the end of the century, percentage of rainfall around the globe. And here it's less clear the patterns relative to the temperature, where everywhere it gets warmer in the global warming scenario. But with rainfall, some areas get wetter, some areas get drier. And in fact, the whole hydrological cycle appears to become more intensified in a warmer climate. With areas which are normally moist, like Northern Asia, Canada, northern parts of the US, and the tropics becoming wetter in a warmer climate, and subtropical regions which are normally dry becoming drier. What's also interesting, the little black dots here on the plot is where 90% of the climate models agree with each other, where we have much more certainty in the results. And I live in the Middle East here, where most of our rain is December, January, February, which models imply it should get drier. Drier, we would have less thunderstorms, but based on that paradox we just saw, maybe that means more lightning in the future. So maybe in the Mediterranean, we will actually see less thunderstorms, more active thunderstorms, and more lightning. So we will see whether this is true. We need to wait. We don't have enough data at the moment. Now, what about aerosols, particles in the atmosphere? This can also influence the lightning activity, and it's expected that maybe aerosol loading will change in the future. If we have a more polluted atmosphere, how will that impact thunderstorms and lightning, irrelevant of the temperature? Well, we know that all cloud droplets form on cloud condensation nuclei, what we call CCN. Without particles in the atmosphere, we would have no clouds. So we have to have particles in the atmosphere to generate droplets, and every droplet that forms in the sky forms on a cloud condensation nucleus. The same with ice crystals. We need ice nuclei to form ice crystals, although there are other ways we can have ice multiplication in storm. But again, without the initial nuclei, we wouldn't have any clouds, no ice, no droplets in the sky. Now, when we have low levels of CCN, of cloud condensation nuclei, then, for example, in this clean atmosphere over the ocean on the left in this diagram, each droplet gets lots and lots of water vapor condensed onto it, and they grow quickly, what we call the warm rain process, so they remain liquid droplets, and because of their size, they fall out of the cloud fairly soon, and we get warm rain, we get rain fairly quickly. This is kind of tropical rain, which doesn't really go into the ice phase that much. But if we increase the number of CCN in the cloud, then we have a lot of competition between the particles for water, and they remain a lot smaller. And if they're smaller, they're also lighter. And so they get transported up with the winds into the upper portion of the cloud where the temperatures are below zero. They can freeze into ice crystals. And the process of condensation and freezing releases latent heat, which warms up the cloud more and can cause the cloud to become more unstable and extend higher up into the atmosphere. And for electrification to occur, for lightning to occur, we need a combination of supercooled droplets, ice, hail, grapple. All of these have to interact together in what we call a mixed phase region between 0 and minus 40 degrees in the cloud. The mixed phase region is where we can still have liquid droplets. Even below 0 degrees, we have liquid droplets, but we can also have ice and hail. And we know that this is where the electrification starts. Without ice, we have very little lightning. And so, as I mentioned, one of the reasons we may not have much lightning over the continent is because mainly it's warm rain processes, not much ice in these clouds. If we increase the particles over the continents, we get a lot more convection, we get a lot more ice, and we can produce lightning. But in the future, if we're going to warm the climate and change maybe air pollution, aerosol loading in the atmosphere, how will that affect the lightning? Maybe that'll also result in an increase in lightning if we increase the aerosols and have even smaller droplets. So we tried to look at this, and we did a study over the Amazon jungle to see how aerosol loading of the atmosphere impacts lightning. We looked at, if you look at the map in the top left, the shading represents the aerosols or the aerosol optical depth measured from the MODIS satellite. And these aerosols are mainly from biomass burning, forest fires over the Amazon. The contours show something about the lightning activity. And we looked in this white box, which is at the border of the smoky area and where we have the thunderstorms and the wet region. And we basically looked at how much lightning we get in the different years from 2006 to 2009, in different months of the year, and how much lightning we get here relative to the aerosol optical depth inside this box. And we see something interesting. We see that initially, in a very clean atmosphere, when we increase the aerosol optical depth, we increase the amount of particles, we do see an increase in lightning activity. And this is this effect that we're getting smaller droplets because we have more CCN, and so we have cloud droplets which are going up, higher up, freezing, producing ice, and we're getting this ice factory which produces electricity. And if we pass a certain threshold of about 0.25 in the aerosol optical depth, then we start to see a decrease in the lightning activity. We have what we call this boomerang effect. First it goes up, but if we get too dirty, if we have too many aerosols in the atmosphere, then the lightning will decrease. And how do we explain this? Well, the first increase I've already mentioned, that we have likely a microphysical effect here, that we, in a clean atmosphere, if we add more aerosols, we actually result in smaller drops, which are lighter, which go up, we can freeze and produce more interactions between ice and droplets and hail and produce the electricity. If we have too many aerosols, like we see here in this image on the right, which is a very smoky background with small clouds, what happens is we have a layer of smoke somewhere, or aerosols, which will absorb some of the solar radiation. And they result in this warming of the layer because they're absorbing radiation from the sun. And then the lapse rate will actually become more stable. If this is the adiabatic lapse rate, the dry adiabatic lapse rate, which is 10 degrees per kilometer, cooling as we go up, we cool 10 degrees every kilometer. We need this is a new kind of a neutral atmosphere. But if we have a slower decrease in temperature, then the atmosphere is stable and we won't have thunderstorms forming, we won't have any convection. So when we have too many aerosols, we can actually choke the thunderstorms and reduce the lightning. And so the link between climate change, aerosols, and lightning is not that clear yet. Could go that aerosols in clean regions will actually enhance the lightning activity, but areas which already have lots of aerosols and get more aerosols, we actually may decrease the lightning activity. Now, is lightning itself important for climate change? we've spoken about how temperature and future climate change may impact climate, but what about the lightning itself? Well, the answer is yes, it is important through tropospheric chemistry. And that is because lightning produces a gas called NOx, or nitrogen oxide. The X can be either a 1 or a 2, NO or NO2. And this is produced because in the lightning channel, we have extreme temperatures, up to 30,000 degrees, which basically dissociates all molecules in the atmosphere and leaves us with atoms which can then recombine into new materials like NOx. And NOx is also a precursor of ozone in the atmosphere, and we know that ozone is a greenhouse gas. Here we can see the bottom left, the flight of a plane which goes flying through a thunderstorm. The dashed line shows us the water vapor, showing that it's going into the cloud, and these spikes represent the NOx measured in the cloud, showing the spikes, which is the increased concentration of NOx nearby a lightning discharge. On the right-hand side, we can see vertical profiles for different places in the world: South Africa, Brazil, New Mexico, Colorado. The x-axis shows the NO, or the NOx concentration. And here too, we see fairly high concentrations in the upper portions of the anvil of the cloud, around 10 kilometers, also close to the base of the cloud. The NOx gets redistributed with the updrafts and the downdrafts, but we get lots of NOx produced in the clouds due to the lightning discharges and the processing of the air that we have inside the clouds. So if we look now, and this is a model study of how the lightning can influence the ozone in the atmosphere. So this is the contribution of the NOx sources to the ozone concentration in the atmosphere. Each of these panels represents a different type of source. So here we have the lightning in the top left, but we also have sources of NOx and ozone from biomass burning, soils, industry, transportation on the land, ships, air traffic, which is fairly small, stratospheric production, O2 photolysis, which is mainly in the stratosphere and above. What we see is that in the southern hemisphere, so this is latitude from 90 south to 90 north in each panel, and again, pressure or altitude going up, that when we look at lightning, this is the most important source of NOx and tropospheric ozone in the southern hemisphere and in the tropics. So in the tropical regions, you can see the biggest source in the troposphere, in the lower atmosphere in the tropics, and the southern hemisphere, since we don't have much industry there, lightning is the biggest contributor to tropospheric ozone. And again, tropospheric ozone is a greenhouse gas, traps in heat, and so lightning itself, if it's going to increase in the future, will increase likely ozone concentrations, which is a greenhouse gas, and result in a positive feedback, accelerating the warming of the atmosphere. In addition, lightning and thunderstorms in general, not just lightning, but thunderstorms themselves act as huge vacuum cleaners, sucking up lots of moisture into the upper atmosphere, which ends up as ice in the upper troposphere. It can be up to -60 degrees in the tops of clouds. And these eventually sublimate these storms, clouds and the anvils, and will deposit their water vapor in the upper atmosphere. And water vapor itself is a greenhouse gas. So changing the amount of water vapor in the upper troposphere is also very important for climate feedbacks. And this can also enhance global warming. So if thunderstorms in general are going to change in intensity and frequency in the future due to global warming, this could also result in more water vapor in the upper troposphere and maybe lower stratosphere, which can actually have positive feedback and amplify global warming. There have been numerous studies looking at the link between the actual lightning activity, upper tropospheric water vapor, clouds, ice crystal size, ice water path. And so there's many links have been found between the lightning, which is a kind of diagnostic of the activity of the storms, and other parameters which are important for climate change. So here you can see this animation of a satellite image showing the distribution of water vapor. This is in the mid-troposphere. And we can also see the white regions are where we have thunderstorms along the ITCZ, so deep convection, like in the little part you can see at the bottom left, showing a picture from the space shuttle, I think, of these deep convective storms with the anvils of ice, which eventually sublimate and deposit their water vapor in the upper troposphere. And the gray region over here, we can see wherever it's lighter gray, we have lots of water vapor. The black regions are where we have dry conditions. And we see that most of the water vapor in the upper troposphere is taken there by thunderstorms and deep convection. So the thunderstorms act as these large vacuum cleaners, sucking up moisture from the boundary layer and depositing it in the upper troposphere, where it can remain for a long time, either in the gas phase or to recrystallize into cirrus clouds, which can also have a positive feedback. And so again, lightning can give us some kind of a diagnostic of the amount of convection and thunderstorms, the intensity of them in different locations of the world. So we looked at this over Africa again, using our lightning index from this Schumann resonance, which I don't want to go into details about that. But some people can read this paper, Bryson threw in 2006. The black curve here represents the day-to-day variability of lightning over tropical Africa. The red curve represents the specific humidities. This is the absolute humidity in grams per kilogram or kilogram per kilogram of air at 300 millibars. And it's actually astounding, the agreement between these two curves. But I should point out that the red curve has been shifted by 24 hours to show this agreement. The red curve actually peaks one day after the black curve, implying that we have lightning activity instantaneously, say today. It takes about 24 hours for the anvils to sublimate and be transported away from the convective regions for us to observe, see the maximum in water vapor in the upper troposphere due to the thunderstorms. So the red curve actually peaked one day after the black curve, but the correlation coefficient between them, you can see, is 0.91. So it's quite amazing. And the sensitivity here is that for every 0.1 gram of water vapor per kilogram of air change that we see in the upper atmosphere, this is equivalent to a 26% change in the lightning index. A very nonlinear relationship. A very small change in the absolute humidity is associated with a big change in lightning. So we can actually use the lightning as a very sensitive tool of how water vapor may be changing in the upper troposphere. So I would like to summarize. I'm going to finish here and basically say that the climate system itself is driven by many factors. It determines, say, the surface temperature at different locations of the planet, different tropics to the mid-latitudes, different over the oceans, over the land. The climate also will determine the lapse rate, whether we have subsidence in some regions, stable conditions, or instability in the atmosphere. And aerosols are also a factor in forming droplets in ice and the electrification process. So we have different aerosol loading depending whether we have biomass burning, we have desert aerosols, we have air pollution, sea salt, etc. These three parameters we've shown in different studies are linked to lightning activity and thunderstorm activity. There's a direct impact of surface temperature, the lapse rate, which may change and affect the thunderstorm development, the aerosols over the Amazon, which depending on how much aerosols have different impacts. The thunderstorms and lightning themselves have an impact on the generation of NOx, nitrogen oxides, which are a precursor of ozone, and ozone is a greenhouse gas. Upper tropospheric water vapor changes depending on the intensity and location of the thunderstorms. So thunderstorms and lightning can actually drive the changes in water vapor in the upper atmosphere and even lower stratosphere. I haven't spoken about it in the talk here, but we've also studied together with David Rind the effect on fires, because in many, especially high latitude regions, like in the high latitude Asia, Siberia, Alaska, Western Canada, many fires are ignited by lightning. And so changes in the climate and lightning can also affect fires. And these outputs here of the thunderstorm can actually feed back on the climate. So the NOx and the ozone can affect surface temperatures. The fires can affect the aerosols through the particles they emit, but they can also affect the greenhouse gases. and therefore they can feedback on the climate. And today, the climate's not stable, so the climate keeps changing at the bottom. And so now all of these are kind of changing continuously and interacting with each other. So today we have to worry about the increasing greenhouse gases, to add another factor here, how this is driving the climate, how that affects the lapse rates, the aerosols, surface temperature, how that will affect the lightning and thunderstorms, which produces the NOx, the water vapor, fires, and this feeds back on the climate. So with that, I'm done, and I'd be happy to answer questions if you have.
Thank you, Colin, for that terrific presentation. Really interesting research that you're working on. I have just a question or two here that I'd like to ask. The first question, and this is from David, as climate models go to finer resolution, eventually they will be able to better resolve mesoscale convective complexes and perhaps even individual thunderstorm cells. For forecasting future changes in lightning, how important are processes on this fine scale relative to those that are associated with the overall atmospheric structure? In other words, will finer resolution and modeling bring about great improvements in our ability to forecast future changes in lightning?
Good question. I'm not sure the answer. When we look at obviously weather forecast models like the WRF model, the WRF model, to try to predict thunderstorms, and we definitely see improvements in the forecasts of thunderstorms when we include all the microphysical processes, the charging processes that grapple in the models. And so on the short time scales, we do see an improvement on weather forecasting. On the climate scale, it's difficult to say. We're still trying to look for large-scale parameters, other large-scale parameters, to try to improve large-scale parameterizations of lightning. We have a study now which we're publishing looking over Africa, trying to use other indexes like the lifted index, specific humidity, CAPE, which are calculated in GCM to try to give a better estimate of not necessarily the lightning, but the thunderstorms. So there's a difference in trying to calculate how many thunderstorms we're going to have in the future on the whole, relative to trying to calculate the actual lightning activity in the thunderstorms. I think to get the estimate of the actual number of storms, the thunderstorms and convection, I think the large-scale parameters may be doing a fairly good job, and I'm not sure if the microphysics will make much of a difference. But if we want to actually really know the amount of lightning activity in those storms, the types of lightning, lightning in the cloud and cloud to ground, then I do think having the microphysical parameters will make a big change. I just don't know if it's possible, because you need to get to very fine scales to get all the microphysical parameters, and to do that on a global scale seems at the moment impossible.
All right, just one more question here. To get the best possible understanding of lightning in both the current and future climates, would it be important for climate models to explicitly include calculations of ions, the electromagnetic field in the troposphere? And do you believe that's even possible to do?
Well, there's been also some ideas that cosmic rays are one way of triggering lightning. You have a cosmic ray going into a thunderstorm, and it generates a lightning discharge, which we don't have in climate models. Although other models can show that based on cloud microphysics, without the ionization from cosmic rays, you can still get electric fields which are large enough for producing lightning. So I think we know quite a lot about charging of clouds. There's still a lot of things we don't know, because it's difficult to go into the thunderstorms to collect data and to do research there. Most of our knowledge is really from lab experiments. But I don't think that we need to actually model the electromagnetic fields produced by the lightning and the ionization in the clouds in order to get the correct estimate of the thunderstorm and the lightning activity. I think the dynamics, the microphysics, the instability of the storm is enough. I don't think we need to go all the way with all the electromagnetic fields and ions. I think it's maybe just too much information, cause more noise than anything else.
Thank you. And thanks again for participating in today's webinar.
You're welcome.
Okay, so that concludes the presentations for today. As always, they will be posted on the CC Run website and available at the same page where most of you came to register and join the webinar. But thanks again for joining us, and our next webinar will be in March. Thanks again, everybody.
Thanks, everybody. Bye.
Thank you. Bye.
Bye.
So the